Welcome everybody to the SIAM Activity Group on Geosciences webinar series. Today we will welcome Professor Eileen Martin from Colorado School of Mines in the United States. And she will talk about how lossy compression makes seismology easier and faster, but a little less accurate. You can't have it all. But before I get going, I would just like to do a couple of notes on general information on our activity group, if you will allow me. So first of all, our announcements are done on Engage, SIAM Engage, as well as LinkedIn. I think on LinkedIn, in the past year, we started LinkedIn and we're a little bit more active. So I invite everybody to actually go and follow the posts there. Other than that, both SIAM and our activity group on geosciences have the membership information online as well as a wiki page. So that is true for pretty much every activity group. Now, I do always point out that if students have a way to have a free membership. So if you're a student and you're watching this, or if you're interested in joining SIAM, there's a way for anybody senior to nominate you and you will get a free membership. If you have any doubts or questions, feel free to contact any of the officers and that can be resolved. Further, before we actually get into presenting Eileen Martin, we point out that we have these pretty regular once a month during the semester. We do try to thread this time that kind of can meet multiple audiences across different continents, but that is we understand that is hard. So this webinar will be recorded and posted on our YouTube list for the later enjoyment. You can always use the registration link for all of them to sign up. And in April and May, we will have talks by Dr. Mantica and Arbogast. So now let me reintroduce our speaker, Martin, Professor Martin. So she's currently at Colorado School of Mines. She's an assistant professor there and runs a group that works at the interface of applied mathematics and geosciences, specifically for seismology problems and remote sensing in general. Has a lot of accomplishments, but her best and biggest accomplishment as far as our group goes is that she is the winner of our Early Career Scientist Prize, and it was presented to her during our conference in 2023. So without further ado, I will let her take away. If there are any questions, you can post them in Q&A or raise your hand. Also at the very end, you can use chat only for saying hi, but for any questions, post them in Q&A. Also at the very end, I will basically unmute you and you can ask your question in person if that is applicable. With that, I am going to stop sharing, and Eileen, if you can share.
All right, let me share my screen and we'll get started. So thanks for joining me today. We're going to be looking at sort of this tool of lossy compression as one of our ways of making seismology easier and faster. And when I talk about seismology, it's really from this kind of perspective of looking at a bunch of different kinds of seismic data. It's not just active source seismic. So sometimes we're recording what's going on in our cities around our infrastructure, like over here on the left. Sometimes we're recording things like trains or trying to use that to maybe even look at like groundwater, using that energy from what's generated by our infrastructure. Sometimes we're using earthquakes over here on the right. Sometimes it's induced microseismicity, like from geothermal fields, like what you see on the far right, or kind of down in the bottom right, there's some induced seismicity from a mine that I work in. And the work that I'm going to show you isn't just stuff that I've been doing. It's a lot of work with Hafiz Issa, who's one of my current PhD students, as well as some work I did with Joseph Kump, who was one of my master's students. He's now over at University of Texas, Austin, doing his PhD. So here's a few examples of the types of seismology problems that I'm really excited about. Sometimes I'm looking at how do we map earthquake hazards in cities. In fact, we've found that these kinds of earthquake hazard maps actually should have a little bit higher resolution than what we typically consider, but it's really hard to do seismology in cities. And so we have to kind of find ways to use new sensors like these fiber optic cables that are just underground in our telecom systems to be able to collect that data. Sometimes we're looking at how do glaciers change and what are all the different ways that they sort of crack apart and slide and move and what are all the noises that they make along the way. I've been lucky to work with a group at ETH Zurich that collected data on Rhona Glacier up in the Swiss Alps, and so that's been a really exciting kind of application for our group. We're also looking at how do we make underground mining safer, and so we have to use kind of new types of sensors underground so that we can even put them under there. But we're able to collect a ton of earthquakes that happen as part of the mining process. And by being able to characterize these little earthquakes, it gives us a bigger and sort of a more complete picture of what's going on in the stress state of the mine and how things are progressing and whether the situation will continue to be safe or if adjustments need to be made to continue to ensure a safe operation. And our group is also working up on the North Slope of Alaska, looking at how we can kind of map out fine-scale permafrost thaw processes. We get complete changes in our ground from being like wedges of ice to sort of ice embedded in permafrost soils, to having thermokarst lakes, all these kind of things over just the scale of a few meters. And we know that that's just what we see at the surface, but being able to look down deeper into the ground can help us to actually get an earlier warning about whether there might be future issues for infrastructure, homes, and things like that that are built on top of the permafrost. So these are the kinds of applications that I'm really excited about. Unfortunately, none of these applications have tons of money, and none of them really have tons of computing resources to throw at our data when we're able to collect them. And we're working under a lot of these kind of constraints. So we're looking oftentimes at really large data sets because we're looking at fine scale processes over really large regions. We look at broadband signals. Sometimes we need both very low and very high frequency signals at the same time. Oftentimes we're also trying to do things like continuous analysis. So we can't just collect our data and then we bring it all back to our HPC cluster and then we can analyze everything all at once. Instead, we're collecting data for years on end, and we'll be collecting data for the entire duration of many of our projects, such as our project up in Utqiagvik, Alaska. So we need to have fast ways to actually collect and learn from that data as our experiment is ongoing. We're also working usually with pretty small teams. If you look at an oil and gas company, they might have, a whole floor of seismic processors with lots of expertise, lots of training, to be able to work on that kind of seismology data. But for these applications like glaciology, cryosphere problems like permafrost, mine seismicity, even earthquake hazards, we have relatively small teams, just a few people doing all the field work and the data analysis. So this need for automation and really robust results when they're automated is really important, as well as the need to be able to give ourselves some immediate feedback as we're in the field setting up our experiments. So when we're dealing with these small teams, we can actually start to learn from the data and see, is it any good or do we need to make changes while we're still out there? When we look at how these things are going to get deployed at large scale, for instance, things like mine seismicity studies at mini mines, or things like earthquake hazards across maybe the entire west coast of the US, it's very unlikely that we're going to be able to have a seismologist or a computational geoscientist at every single one of these sites analyzing these massive data sets that we're collecting. And so we need to be able to have this kind of ability to have computational methods that can be operated by people with relatively limited expertise. And many times we're working with sort of new sensors in these kinds of new environments. But these kinds of new sensors are opening up these new avenues for research, but they're also creating some challenges on the computational side, which is cool for me because I like big data sets. They help me get motivated to work on interesting, fast computational algorithms. But it does mean that a typical environmental scientist or civil engineer might struggle to use these data sets. These kinds of new sensors, they're sort of part of a larger trend of working with lower cost sensors, but where you have many sensors that can be put out. So this might be things like using cell phone accelerometers as seismometers, being able to use what we call small nodes or lightweight nodes. Here's a little backpack down in the bottom left where, one person can carry like 60 sensors out on their backpack easily. Previously, seismic nodes, you'd be doing pretty good if you could carry like 6 or 8 out per person. So we're really getting these orders of magnitude more data that we can collect with these new sensors. And I work a lot with fiber optic distributed acoustic sensing, which is shown here in the middle. It's just using standard fiber cables that you would use for telecom. But by measuring those with an optoelectronic system, we're able to actually tell how much is that fiber vibrating at every single point. And today we have sensors that can measure over 100-kilometer sections of fiber optic cables every, say, 10 meters, or even some systems go down to a meter. The resolution is improving and the distances over which we can measure are improving. And so this means bigger and bigger data sets by several orders of magnitude. And just to put that in perspective, I took a handful of maybe 9 experiments that me and a few colleagues and collaborators of mine had done over maybe a 5-year period, not even all the experiments that happened in that 5-year period, and just academic ones where we were under more constraints than, say, an energy company might have. So these are still relatively modest scale. And we collected something like 800 terabytes of data during that time, which was actually bigger than the entire data management center for the seismology community that's sponsored by NSF. And so right now, we're actually in a position where the seismology community that's starting to use these new sensors are unable to submit our full data for reproducibility to our public archives simply because there aren't the resources there to support it. So this helps to motivate us to think about things like how do we compress our data so we can at least share it in a format that's usable to people when previously it would have otherwise been inaccessible in its raw form. So one way we can do this is with what we call lossless compression, but that can't really get us more than about a factor of 2 compression. It's not enough to make it feasible to start sharing all of our data publicly, and it's not enough to make it small enough to be really interactive when we're trying to do data visualization, interpretation, that sort of thing. And so we turn to lossy compression because we're able to get much, much bigger compression ratios on our data. So our data are approximately represented. We're able to get these higher compression ratios. And specifically, my team has been looking at things like 1D wavelets, 2D wavelets, a compression scheme called ZFP that was created by Livermore Labs, and then truncated singular value decompositions, among a few other types. But these are ones that I really like because they're things that we know how to actually express what our representation of our compressed data is in a way that allows us to actually think about how can we do maybe different kinds of operations on those. Can we think about what's our error propagation through our different types of analyses? And can we start to even do our analyses in these different compressed domains without ever having to decompress it? So I'll kind of speak to these 2 issues of how much error is going to happen when we do this for certain kinds of analyses. And then also, how can we take some of those types of seismic analyses that we want to do and actually do them in this compressed domain to keep our memory footprint as small as possible. And that's really important if we're trying to sort of work with really limited computing resources, especially in those scenarios where we need to get some kind of understanding of our large data in the field. So here's a few scenarios where this comes up. And depending on the scenario, we actually go for different approaches on what we would actually use lossy compression for. So for instance, going from our field site out to our office, sometimes we have team members who aren't able to come to the field with us, but they could provide a lot of expertise on reviewing the data early on while other team members are still working on the experiment on site. So can we send the most meaningful subset of our data back to larger computing resources or to people who have other expertise so that we can start to get some initial analysis and feedback? So that's one constraint that we have. Some of our issues there do get overcome by being able to use new systems that are coming up like Starlink, as opposed to having to just use cell phone telemetry when we're in remote areas. But it's actually not enough for many of our data sets still. So we still need to be able to compress by a certain factor there. Sometimes we're just working on our laptop or our desktop computer, and we want to be able to reduce our file input and output or I/O time for interactive visual exploration of our data or kind of tuning our processing schemes as we go through. I work with a type of data oftentimes where we just continuously record random seismic junk. It's called ambient seismic noise. And with that kind of data, we actually have to tune our pre-processing workflows a lot before we can actually start to get meaningful information out of it. And so being able to actually interact is very important for being able to get that work done on a reasonable timescale. Also, as we're thinking about those public seismology data archives, many of those are moving into a cloud system. So the Department of Energy's geothermal data repository has already moved over into a cloud system. And when we're looking at the Earthscope repositories for what we have called IRIS DMC in the past, that's actually moving into a cloud system as well. And so when we're thinking about how people interact with those cloud systems, many scientists might not actually need to download massive data sets to their local computers or even need to load them onto other compute instances all the way. If we can have sort of multi-tiered storage for those where we're able to have compressed versions that we can very quickly analyze data products on, this can help scientists to actually narrow down which data do they want to fully analyze before actually requesting that that gets moved. And that may help us with being able to actually afford to support these public data archives as we move forwards. So there's these trade-offs, right? We want to be able to get faster data movement. We want to reduce our storage space. We want to have faster data analysis. But when we're dealing with lossy compression, the kinds of things that we're worried about are we going to lose detectability of our seismic events, especially the small ones that might help us delineate maybe faults or weak zones in our rock? Are we going to be able to have reliability of the timing of our events? What if the compression were to shift over the time when we think that our event is arriving, and suddenly that makes us infer the wrong seismic velocities in the subsurface? We might actually see some kind of change that's not even real. So we worry about that a bit. We want to know, are our results going to still be accurate? And also we have some concern about, as we move forward into the future, how simple are our methods? Sometimes if we're trying to operate on data in a compressed domain, if it's too complicated to express that data and that operation in that sort of compressed domain, it could actually be really hard to maintain our software in the long term, or to port it over to new hardware and take advantage of new hardware as it comes along. So we actually have those trade-offs as well on sort of long-term maintenance of our methods. So here's one example of one of these data sets that I've been involved in. So this is the 4C data that was collected on the Penn State campus. I helped my friend Tian Zhu set this up, where we've got fiber optic cables that are going just all around campus, the existing telecom network. You can get all this data off the Penn State Data Commons or off of the PubDAS repository that an Air Force project I'm part of has put up. And we can see that there's a lot of different sensor locations. Here we've got over 2,000 sensors in this area, spanning about 5 kilometers worth of distance. So every 2 meters, we have a new sensing location. And here's a minute's worth of data during a thunderstorm. And you can see all these like thunderquakes. There's all kinds of signals in this area though. And so we wanted to be able to say like, well, how much does this sort of change if we do different types of compression? And so at its most basic level, we just said, okay, this is passive seismic data. Let's take, a day or more of data and let's look on average at how much the raw data itself is changed just to start with. So we just did simple time and space domain differences to get a basic handle on these compression types. And when people have been looking at lossy compression historically, this is kind of the standard test that they'll do. They'll just say, oh, here's your data before. Then you compressed it, then you decompressed it, and here's your data after that was reconstructed. Here's the difference. So this is our starting point. So in general, we saw that for compression factors that are kind of less than about 20x compression, we tend to get a really good response from our ZFP compression. ZFP is basically breaking up our 2D data into little 4x4 blocks, doing some quantization on different pieces of it. There's a continuous or a discrete cosine transform in there as well. And so it's got basically this sort of assumption of some continuity within these little 4x4 blocks of our data. And that just means over an 8-meter region and a tiny fraction of a second, maybe like 4/1000ths of a second, we have some continuity on our seismic data. And generally that's good enough for us. And so we see that it's performing quite well here. As we get to these larger compression factors, we tend to see that 1D and 2D wavelets actually do start to outperform ZFP. And especially 2D wavelets give us lower errors in general than 1D wavelets do on data that's inherently 2D. And that's totally in line with what people have seen with other types of 2D image data. We see in general, like our singular value decomposition that's truncated, it's never the best, it's never the worst, but it's just kind of this nice little, like slowly ramping up error that happens. So it's at least pretty predictable. We don't get sudden changes in the amount of error that gets introduced as we slightly tweak what our compression factor is. So, okay, this is kind of our basic stuff. We also looked at our frequency domain changes in our spectra and generally didn't see too much that was surprising there. One thing that does come up that's important to be aware of is in the ZFP compression. Because we have that discrete cosine transform as part of the step there, we actually do see some artifacts at certain frequencies there. And so that is important to be aware of, even though it can give overall a lower normalized error in the time and space domain. Okay, so it's nice to know kind of like generally how these compare on our raw data, but actually I don't care about raw data at all. I care a lot more about, are my results going to change? Are the things that I'm going to learn from this data going to change? And so we've been trying to choose a few key workflows to really dig in on these kinds of questions. So how detectable are the same sorts of seismic events? Is there any denoising going on that might allow us to even detect new events? This is kind of a well-documented thing with wavelets or singular value decomposition that you can get some kind of denoising effects when you're also doing compression slightly. And we also want to know if we pick the arrival times of our events, are we going to change what our arrival times are if we have a compressed version of our data? So we started off looking at this with what's called the Brady Hot Springs experiment. This was a geothermal site that the Porotomo team had worked on. There are folks out of University of Wisconsin, some of the national labs. And they created this whole fiber optic array that you can see the geometry of here on the left with more than 8,000 sensing locations spread out across this big field right above this geothermal area. And all the data is available publicly. All the stuff I'm going to show you is reproducible and our codes are all out there. And there were a few earthquakes or seismic events that were noted initially, but then Lee and John in 2018 showed that you can really drastically increase your number of events by doing this process called template matching. It's basically a cross correlation or a convolution that's been normalized between existing events that you know about that might be larger and all of your continuous data. And all that continuous data kind of looks like junk, but if your existing large events are relatively similar in their shape to any piece of that continuous data, even if it's a really weak event, it might be able to bring that event up over our sort of noise level so that suddenly you can pick out more of these events. We see a lot of events that they had found. And we wanted to think about like, what can we do with compression to actually make this faster? And in particular, to what extent is this catalog going to be affected by using compressed data if someone were only able to download that smaller amount of compressed data for even just their initial investigation? So we use this template matching. We take this small number of events. Here's an example event called a template up here on the top, and it's just a fraction of a second. You can see pretty clearly that there's some kind of move out across this array as this event hits all the different sensing locations. And then we do that normalized cross correlation of each channel with its own continuous recording. And when there's actually an event, what we see is that these cross correlations actually all kind of light up at the same time, or at least the same time lag for these different channels. Even though they all got the arrival at different times, this cross correlation is very easy to pick out as these vertical lines in this kind of image here. We followed the exact same workflow as Lee and John. We weren't trying to reinvent the wheel on microseismicity detection, but we did want to know, when you follow that workflow, how different is it before and after these different types of compression? So as we looked at these different types of compression, we've got 3 different categories of compression that we're looking at here. 2D wavelets on the left, ZFP in the middle, that's those 4x4 blocks, and then on the right is our truncated singular value decomposition. And for each one of those, we had between our original data and all the way up to 100x on some of them, only up to 45x on ZFP compression. That was the highest compression ratio that the options allowed us to have. in general, we actually see 3 events there. And from looking at our raw data, I never would have picked out all 3 of these events, maybe just the biggest one, definitely not this mid-sized one or the smallest one. I've got these purple, blue, and red arrows to indicate when those happen. Overall, we see that the wavelet compression sort of maintains the most consistent amplitudes of when those events are happening between our compressed data and our original data, even for our very high compression ratios like 100x compression. ZFP, we can still get most of our events. Our mid-size event we can always get, our largest event we can always get. We do see some degradation in being able to pick out those amplitudes. That means it might be detected a little bit weaker. And our weakest event, I would not say is detectable at all at our 45x compression ratio. It's still able to be detected at about 34x though. So we can get pretty good compression there for those sort of smaller, but not the highest compression ratio. And then when we're looking at our singular value decomposition, we actually see pretty substantial energy loss, especially at our 50x and 100x compression ratios. But we know that we can at least get sort of 20x, and we're still seeing those events quite clearly, even the smallest one. For some sort of reference here, for the study that I'm doing up in Alaska, where we're very limited on our bandwidth from the field out to our offices in the rest of the US, we can't have our team up in Alaska all year round. And so there we found that for our limited bandwidth, we needed to have about 20x compression to be able to actually transmit that information. And so this is kind of, any of these choices would be in line with that. Okay, so as we start looking over sort of these different compression ratios, it's a little hard to eyeball those different envelopes of our cross correlations. So we started looking at what's our detectability or our detection significance. And for this, we were able to look at all of these events. So event 3 is our biggest event. Event 2 is our smallest event. And then event 1 is our mid-sized event here. And we see in general that wavelet compression, we get really consistent detection significance. And so that's really important for us to know, that seems, even at these very high compression ratios, to still be significant by our quantitative metric of significance. So we're always exceeding our threshold for picking these events. With ZFP, we're getting relatively consistent detection significance, but somehow, as we get up to these slightly higher compression ratios for our largest event, it does actually get a little bit of an uptick. It's not to say that's good or bad, it's just a change that you might notice. And then when we're looking at our singular value decomposition, we do see this pretty substantial drop in our detection significance, and especially for our smallest event that was already kind of on the borderline of whether it would be picked or not at that threshold indicated by the brown line, we see that pretty quickly at about 10x, it already has dropped out below the detection threshold for this particular study. So we have these risks of losing some of those small events. Now, if your goal is to pick out events that are the largest and the cleanest and maybe some mid-sized ones so you can do some imaging, then maybe this is fine. But if your goal is to get sort of precursors or very small signals that might help delineate slightly weak zones, then having these small events drop out is more of a concern. So it really depends on your application needs. And when we look at the entire catalog of this whole study, we see in general that wavelet compression here on the left, we are showing our detection significance of our compressed data on the vertical axis, and then our horizontal axis is our original detection significance. And we see relatively little change. It's mostly staying along that 1-to-1 line there. But we do see at these low detection significance levels that at 20x and 50x, those red and purple dots, we are starting to get some drops there. So we are losing some events down there where they're getting quite a bit smaller. On our ZFP compression, we see a lot less continuity in our trends overall. It can be a little bit less predictable how that's going to behave than our SVD or our wavelet decomposition. And we see like some loss of our detection for these larger events, which was surprising to me. I thought that these very well detected, strong events up in this 150, 175 detection significance level, I did not expect them to drop nearly this much. And so that was surprising to me. We were a little surprised in a pleasant way for SVD, actually, that up at the larger events, we actually do get some of that cleaning up happening or a denoising. We see that we get better detection significance at some of those high compression ratios. But for some of these weaker events, we do start to see pretty substantial drops in our ability to detect those. So we also note that, like, if you're just interested in large events, SVD can be a really good compression tool because it's going to also clean up your data a little bit and maybe bring out those big events if that's all that you really care about. And the only thing that is a limitation of just being able to detect the events is usually that's followed by a question of exactly when did each of these events hit each one of your sensors. That's how we actually use those seismic events to start imaging the subsurface, or to really localize where those events occurred. So those are our two sort of typical cases. And in both cases, we want to know what's the peak time of exactly when that event hit each location. So for each one of our compression ratios, for wavelet on the left, ZFP in the middle, and SVD on the right, we've gone through our small, middle, and large size events and been able to do this comparison of how much is the peak time changing. So we basically got, for each compression ratio, for each type of compression, we look at across the entire array with thousands of sensors, what's that distribution? What's our kind of box and whisker plot of our different quartiles and median of those peak times compared to the original data's peak times? And we do see that as we go to higher compression ratios for all of these different cases, we are getting much more spread in those peak times. But in general, we're not actually seeing any change in our medians. They're staying substantially, like, really close to zero change in our detection time. So we're seeing that we're not getting a bias across our array, but we are getting more variance. And so that does mean that we need to have methods that can deal with more variable picks, or we need to use these kind of tools as a way to sort of sub-select which events do we really care about, and then go request that full resolution data just for those events that we really care about. And so we have to use this kind of with caution. And this does tell us, especially with sort of getting up into that 50x or higher range, we're starting to get a lot of spread up to even a half a second or slightly more sometimes. In general, we're seeing that ZFP compression is kind of preserving that largest event peak times at about 45x compression, and that's on par with about 20x compression from wavelet and SVD compression. And so when you're trying to do these sorts of comparisons, hopefully this can be helpful. And if you're interested in any of this, but you want to try out some other kind of compression schemes, some different compression ratios, a different data set, we've got all of our software for this stuff is up on a GitHub repository that Hafiz Issa created. And so you can get all of this. It's all made in a modular way so that it's easy for you to plug in whatever other compression type you might be interested in, whatever other settings you might be interested in. And if you want to adjust the workflows, you can do that as well, add in your own modules. So, okay, now that we know that we can quantify these errors and we can at least know how we say, like, is this acceptable for our workflows? We might also just say, like, okay, let's say that we're fine with this. How do we actually take advantage of it to make our analyses faster? Especially if I don't want to go through all my full resolution data and wait a long time to just get basic metrics of what's going on with it. How can I use a compressed version to really quickly calculate other information about it? So in the past, a lot of people have used lossy compression in scientific computing as a way to kind of compress your large scale data. As you're, reading or writing those files, you have a smaller amount of data that needs to be read or written, which is a slow process. But then you still expand it all out into its full size in memory, and then you analyze data that basically looks like the reconstructed data. It's still pretty large in the memory footprint. But something we've been working on is taking that large scale data, having it be compressed and stored in that form. And so your input and output of your files is still fast. But once you bring it up into memory, you never actually decompress it if you can avoid it. Instead, we want to be able to actually operate on these smaller amounts of compressed data, move less data in memory, and speed up our operations when it's appropriate. So one of the operations we've really dug into for this is what's called cross-correlation. This is the foundation of that template matching operation I was showing in those earlier slides. But it's also what's used a lot for what's called ambient noise interferometry. This is a way of just recording lots of data on tons of sensors and recreating stuff that looks like an active controlled source seismic survey. We have to just cross-correlate signals between different sensors tons and tons of times as they record the same random noises. It's a really expensive process. Like, you can wait for days, weeks, months on your set of cross correlations depending on how big your experiment is. And we don't really want to do that. We would rather be able to start saying which parts of our data are useful and how can we start to get these cross correlations faster. So one way that we looked at this was, what if we represent our data in terms of thresholded wavelet decomposition? So we've got our original time series, we get some approximate version of it. It's represented by some detail and approximation coefficients. And we can actually, represent those coefficients in a vector. And of course, we can say if those coefficients are really small, we're going to threshold and set them to 0, and then we've just got a sparse representation. So this is a pretty common thing to do. And we thought, like, this looks like the kind of operation that we could actually do a cross correlation on in this compressed domain in terms of these coefficients. But if you don't take advantage of certain structures, it becomes way, way more expensive than doing a regular cross correlation of your original data. So we wanted to avoid that. When we wrote out what does this cross correlation look like in the wavelet basis, it looks like almost a tensor with different matrices that get multiplied by sort of two sparse vectors that are both the same. But there's a lot of structure in this tensor that we can actually take advantage of. And so we went through it. We looked at, like, what are all the different sort of aspects of this that we can use to design data structures. And we found that there's a lot of redundancy across time lags. We get these like toplets-like structures, so it's easy to kind of look at how different entries might represent each other without having to actually redo calculations on those or pull up as many entries. We found a bunch of symmetries, redundancies, and subblocks of this sort of tensor. And we also are, of course, able to avoid creating half of our time lags. The cross correlation operation, we can kind of switch positive and negative time lags, so we take advantage of that. And eventually we were able to come up with an implementation that actually brought us down to being quite a bit faster. So here's some results of scalability, depending on what your sort of number of time samples is on the data that you're trying to cross correlate. So that's our horizontal axis versus our runtime. And we wanted it to be like actually a good comparison. So we didn't do our time domain cross correlations. We did a frequency domain cross correlation that's a little faster in this situation. And then we compared beyond that. So with our 10x compressed data, we're quite a bit faster with our 20x compressed. And considering what this would have been like had we not taken advantage of all those different structures of what are our cross correlations of our wavelet basis functions looking like, this actually is really surprising that we were able to get so much faster by doing this. However, this is a pretty difficult algorithm to sort of implement correctly, and we do have concerns about whether it's going to be something that we can continue to maintain or improve on in the future. When we think about how do we expand this to 2D separable wavelets even, the bookkeeping starts to get a little bit nasty. And so it does make us, lean a little bit more towards some types of compression that might lend themselves to simpler algorithms that are just easier to implement. On the bright side, though, we get pretty much the same cross correlation results. Here's some examples of 5x, 20x in our original data. There's also 10x in there, looking at cross correlations of vibrations recorded across an industrial facility. So on the bright side, things look pretty much the same. It seems pretty robust, and we can also do theoretical analysis to tell us like how we can bound how much error there's going to be on each part of our cross correlation results for our compressed versus our original data in terms of what our compression thresholds are. And so that's all very nice about the wavelet transform, but there are these concerns still about sort of the level of complexity of the algorithm, even if it is fast. So we can kind of bound all of this and understand it, which is good, but it does feel complicated. So, okay, we can try to do something simpler. So with data that we feel okay about looking at a singular value decomposition compression of it, we might have some data matrix D over here on the right, where each row represents a different sensor and each column represents each of our time samples. And I've just highlighted the piece of that is really relevant to picking out the data for a particular sensor here. And we can usually compress this quite a bit. We've done some tests where, we can easily do like 20x or more compression and still get pretty good results. So let's say that we go with this SVD compressed version of our data and we want to do a bunch of cross correlations between different sensors. And I've marked those different sensors with maroon and orange here. And then there's some green pieces that just have to do with which parts of the times are we actually dealing with in our data in that factorized matrix. And the reason that we write it out this way is because once we know that we've got to do this multiplication, we can start to look at where are the time pieces, these green bits, and where are the sensor specific pieces, these red and orange bits. And we see that actually there's these little time dependent pieces that are independent of our sensors. So we can kind of break this up into a two-phase algorithm where we just calculate these sort of time lag dependent pieces. We'll call them W's here, they're all green. And then on the outside, we've got this tall skinny matrix and this short fat matrix that are just related to what our sensors are. And so then we can kind of reuse each of these factors for all of our different sensors. And if we start to multiply out a few more of these things, make it look a little simpler, it basically becomes a tall skinny matrix times one of these little bitty k by k factors, if k is much less than our number of time samples or our number of sensors, times a short fat matrix that's dependent on our sensors. And suddenly this also becomes an operation where our scalability is no longer our number of time samples times our number of sensors squared, but now it's our number of time samples plus our number of sensors squared. And that's way cheaper when you're thinking about the fact that our number of time samples goes up so that we can get high, high resolution. And that means that also grows with our number of sensors that are also trying to pick up that high resolution stuff. And so it basically is cutting us down by at least an order of magnitude there. And it also means that this operation is now just like a simple dense linear algebra operation that can take advantage of all our sort of modern hardware, new libraries for dense linear algebra. There's so many people out there that like optimize this stuff, and we want to be able to take advantage of that. So here's just a naive implementation of this on an array that only had like 310 sensors, and we already saw a huge advantage there. We went from something like 174 seconds down to less than a second and a half to deal with this, and that's including our decompression time as well for our original data, or afterwards. We kept about 5% of our singular values there, which tends to be a pretty typical amount on how much we can compress our data for some of these passive or ambient seismic noise studies. And of course, as we get larger, we expect this improvement to become more substantial. So overall, we're seeing that we're able to collect these larger seismology data sets a lot easier, but we need to make sure that on the computational side, our ability to analyze and share these data in public archives is really keeping up. We're also trying to look into lossy compression as one of our possible tools to help us manage that data, to move it around more easily, to interact with it, and just to analyze more data more quickly, as long as we're able to accept some loss in our reliability. We're also thinking about how some of these types of lossy compression and some of these types of analyses are really pretty amenable to having faster algorithms to analyze our data in that compressed domain. And so we're interested in continuing to explore how much can we sort of get our entire end-to-end workflows done in these compressed domains, like our singular value decomposition or our wavelet transforms, that kind of stuff. There's a lot of seismic preprocessing that can be done, for instance, in the wavelet domain. And of course, we're trying this out on all different kinds of seismic data to make sure that we don't kind of over-specialize to just one type of seismology, because we're actually seeing seismology really grow and have an impact in so many other areas of geoscience. So that's all I've got. Here's some acknowledgements for great collaborators and funding sources, all that good stuff. And happy to take any questions.
Thank you very much. This was excellent. So I don't know, I don't see anything in Q&A, but I have some questions.
Yeah,
so
sure thing.
while those who are present gear up with some questions, one thing that struck me is that there is a lot of noise, and it's not that you can avoid noise. So every time you go to a different site, there's different type of noise. There's always this resident noise that is simply there. So when people process data, what is the typical type of filtering? Do you first have some sort of like background image? I mean, these are images, but they're in time and space. Or how do you subtract some noise that is simply present in the environment?
Yeah. So it's really different at every spot. So I'll say, for instance, when I'm looking at this data that was collected in a mine where we're studying mine seismicity, there's tons of machinery noise. And even if I were to go to a different mine, I'm going to have different machinery noise, different size motors, all kinds of stuff like that. I generally know that those look like kind of narrow band signals. So looking over here at this spectrum in the top left that's like kind of rainbow colored. It's got these horizontal bars. And we also know that those are kind of pumping systems. They're probably heating and air conditioning systems on a college campus or plumbing systems, one of the two.
Mhm.
And so for stuff like that, we can do a bit of just like spectral filtering when it's happening. So that's a pretty common one, but you have to be able to identify that those are going on first. And so there are some tools out there, just like computer vision tools, to look for, straight lines, edge detection type
Right.
stuff. And then you can kind of target from there if you want it to be a relatively automated process instead of sort of manually picking out and shaping those filters to get rid of those frequencies. We do tend to get a lot of noise that's called common mode noise on the fiber optic sensor specifically. It has to do with how the optics work in the system that measures an entire fiber optic cable. Typically, we get rid of that just by saying, at every time sample, what's our mean or our median, and then kind of subtracting that off. There are some other sort of adjusted versions of how we can do that as well. They get a little fancier. But we have also been moving a lot more towards machine learning tools for that sort of initial denoising because it can be so time consuming. So at the mine, for instance, my student Ahmad Touré has done quite a bit of work on using autoencoders to sort of tell when are there anomalous events or changes happening as a way to help us sort of explore at least what are those noises that are showing up. So we've got a paper that we just submitted to the ARMA Rock Mechanics and Geomechanics conference on that. And so hopefully that'll all be out soon for people to look at as one possible way to kind of deal with this. Also, my former student, Julius Grimm, and now my current student, Rachel Willis, they've been looking at how you can use unsupervised learning, different types of clustering with sort of physics related and seismology related features to be able to cluster different types of events. And another of these tools to just sort of say, like, what are the types of noises going on? Are there things that are really noticeable where we should be focusing in? So at least we can detect those faster because we collect this continuous data over thousands of sensors, and it's not even possible to look at all of it sometimes. Yeah.
Yeah, it strikes me that is there a public repository that would have some common examples that are like one can use or train
Oh, so I've been
machine
hoping that
learning?
at some point our community can kind of like get it together enough
It's a
to have
hard
some
problem.
like,
I've been doing it on a
yeah,
different type of images. It's not an easy problem, but I'm
it's a
interested
ton
in
of
how.
effort to put this together. Yeah, but at least at this point we do have, there's the PubDAS repository for the fiber optic sensing types of data, and it has a bunch of different types of experiments. So that's hosted on the supercomputing cluster over at University of Michigan, funded by the Air Force. And then anybody with a Globus license, so most universities,
Mhm.
national labs, things like
Have one.
that, you can pull that. Even if you don't have a Globus license, I think you can still get it, but it's just slower maybe. So anybody can at least grab those
Strikes me. So in image analysis in general, the biggest sort of changes were brought in by ImageNet, or these networks where images were labeled or classified. Now they're easier to classify than they're photographs, of course, but still, like you could have an equivalent, trucks and birds. You could have like truck noise, pump noise, right?
Yeah,
So,
yeah. This
and
would
you
be
could have a
perfect.
call to community says, "Hey, this week submit truck noise."
I like that
Possibly,
idea.
right? And then next week submit whatever other noise,
Yeah.
right? So
I wonder,
name your
like,
big machine equipment, and you just have
yeah,
different calls, and then you can use those as classified or labeled in these type of
yeah.
images. Now you will have to use compression before you run anything that is out there already, but
Yeah,
it
yeah, but it
strikes me
could
that
be
it could
like
be
you have sort of compressed maybe a spectral domain image and a
right, right,
time space domain image, and then people have to kind of click on here's the outline of this type of noise. Like,
right.
yeah.
But you could have like a week, do kind of like the theme of the week
Yeah.
collection.
Oh, that could be fun.
Because it strikes me when you immediately said like, oh, well, I can kind of recognize that this is a lot of
Yeah.
trucks or something like that. But you could probably train image algorithms fairly easily to
Oh,
recognize
for
that there's
sure.
something going on.
Yeah.
And at least then you have a guess. And
Yeah.
then
Yeah.
next time you could just say, hey, is there any known noise in this?
Yeah. Yeah.
So go from there. Anyway, it is a
And there's
difficult
definitely
problem.
been a lot of progress on the side of like if there's sort of impulsive events, whether they're tectonic or caused by other sort of cracking sort of things, but they lead to vibrations. There is the sort of, I think it's called DAS PhaseNet, that's already been trained and out there. So at least for some of those categories of events, there's some stuff that's like fully automated now, which is really nice. But like some of these, the vehicles, stuff like that, like I feel like, yeah, it's just got to be a community effort to kind of label all of that. Yeah.
Right. You first kind of need to agree on the verbiage or dictionary that people will use,
Yeah.
but that's a language problem too. So any questions from the participants before I keep talking? I like to ask questions. No? Raise your hand. No? So my next question is also, so this is something that I grapple with in different types of images, those from computed tomography, but essentially an image comes my way. How do I assess quality of the image? Is there something that is like, there's signal to noise ratio in any image, but that tells me and doesn't tell me anything sometimes. How do you do that for the type of images you collect?
Yeah. It really depends on what type of imaging we're trying to do. So we get, of course, our final images, and there's one set of sort of how do we look at, is that good quality for that? But even when we're looking like here, let's say if we were just getting our data streaming in, but we look at it as a picture as it comes in, and we want to say, is this good enough for our purposes? So for instance, here, this is these earthquake events over on the right. You can do at least what's your kind of running background window of what's your distribution versus during these events that are happening, and say, okay, what's your sort of signal to noise ratio there? And so there's at least some simple things to do there where you can say like, well, this is how big this is. But then you also look at things like over on the far left, there's what we call just ambient seismic noise, and it just looks like complete junk. And with that, we really don't know until we've done different cross-correlation procedures and maybe a bit of spectral whitening or normalization in time and space, whether the signals that we get out actually look like active source seismic data, where we could then do something similar to the earthquakes and kind of do a signal to noise ratio analysis, or looking at what are the sort of move outs across the array? What are our inferred sort of initial velocities? And so with those on the left, with that ambient noise, it's really critical that we can start to get those cross correlations across many sensors while we're in the field with really limited computing resources. And those are pretty expensive, but there is another thing that we can do that's a lot cheaper. So we can get sort of an implicit cross correlation, and then at least do the analysis of the velocity in a way that only scales linearly with our number of sensors instead of quadratically. And so that means that that's the kind of data product where if we're looking at these things, we call them dispersion images or tau p transforms. They're kind of like a radon transform of our cross correlations. With those, we actually have algorithms now that are able to be sort of an in-the-field data product computed on our instrument's computer. And then that can be sent off for someone off-site to look at and say, does that look reasonable? Are these velocities that are realistic? Is this starting to break down? Is my data getting worse? That kind of thing. So there's a company, Optisense, that uses an algorithm I had made for that now, so that they can do like some landslide monitoring tests, and they calculate these cross correlations on the field or in the field with just a little resources, and they send it off to their AI system to kind of detect whether the data quality is breaking down. So.
And when you would say this is sort of an ambient image or noise or junk, as you call it, does that mean simply when you try to detect events, there is none?
So there can be events in it. We try to avoid stuff where there's really large events, but as long as the events are kind of uniformly distributed and random,
it's about the
they're
distribution, spatial
independent.
distribution of events.
Okay. Yeah, it's a lot about spatial distribution, making sure that they're not temporally correlated with each other. So like if a car drives by and it hits 2 speed bumps in a row, this actually causes some pretty big issues for us. As opposed to if the car just drove by and didn't hit anything, because these kind of act as a temporally correlated source. And so there's a bunch of assumptions about independence of our sort of seismic wave field, and of the sources that are generating that wave field, that we try to sort of reshape our noise to look more like.
Okay, yeah, that's a lot of manual analysis.
Yeah, and so this is like super frustrating. So this is why a big part of why we're like trying to get these tools to be able to really quickly tell us like, can we even interact with that workflow to change what our pre-processing is or change that process to reshape our data to look more ideal, instead of having to like wait for days to get our results and then see, does that look okay, or do I need to tweak some kind of filtering? So,
Wow.
yeah.
And one more thing that piqued my interest was most meaningful data set. A lot of times in subsurface modeling, you have something called, like I'm calling it representative elementary volume. So I'm working with a volume that seems to be representative of a whole. So in that sense, it's meaningful. What is the definition here for most
Ooh.
meaningful? Or I do
That's hard to-
understand that,
yeah.
like, if it's hard to
I think that
analyze noise, then it's also hard to define meaningful, but
yeah, I would say that for the ambient noise studies, our sort of really meaningful thing is once we've sort of created all these cross correlations and we're happy with our sort of pre-processing scheme, then we have something that looks like a bunch of what we call shot gathers or active source responses across our array. And so that's the kind of data that, like, at that point we can say, yeah, this is good enough to use for imaging, feed it into either a tomography or a full waveform inversion or something like, or maybe a migration, depending on what's appropriate. And so those are the kind of things that I would say are sort of our really meaningful point that we want to always be able to get to. When I look at these data sets that are more about detecting microseismicity and mapping those out, it's really more about, once we have that collection of our catalog events, how can we back project those to say, where are those events happening? Because that's what we use to say, where are the weak zones in the rock? Where have things been fractured, or where are fractures growing? Where might there be safety risks? Yeah.
So those meaningful data sets, that's basically just sort of a time-space subdomain there you're going to focus in.
So it depends on the
Something
setup.
like
So
that?
like on the ambient noise side, it's space versus time.
Okay.
And then sometimes if we're looking at, are things changing over time, like with permafrost, we get huge variability throughout the year. In those cases, we also get a fourth dimension of kind of our time window, maybe this week versus next week versus the next week. So those are kind of a 4D volume. Yeah.
And in permafrost, it's the thawing that kind of releases an event. Like, what is an event in that?
Oh, so in permafrost, there actually we're trying to sort of image whether the properties are changing. So sometimes it's just thaw. Stuff goes from, up in the active layer where things kind of thaw seasonally, and we expect that. It basically goes from ice in the pore space of the soil to liquid water. And sometimes that also means pooling of water on the surface. But there is an interesting thing that Tiwan Zhu, who's a researcher at Penn State that I collaborate with, he looks at how do actually wedges of ice in the ground, as that thaw and freeze cycle happen, how do you actually end up with fractures happening in that? And that actually does release a separate set of events. And those can be used in a different way for imaging.
Okay, got it. So there's
yeah.
fracturing that you could, all right.
There can be, yeah.
I learned
Yeah.
something new. Well, I could sit all day here asking questions because a lot of these things I'd love to know more about. But if there is